Now let's take a look at forced oscillations. So we'll just pay attention to the case when the forcing function is oscillatory, so when it's being driven by some steady sinusoidal wave. So let's see. So first off, if we're looking at the undamped situation, so that's when the equation looks like this one. Then it works out that it's all about looking at does omega match phi, your intrinsic frequency. So again, this is square root of k over m. Okay, so that really determines what's going on. So if we have that omega is not equal to the intrinsic frequency, right? So here, phi is how the system wants to bounce around by itself, and omega is what you're doing to the system. And if they don't match, then it turns out that your particular solution is going to be f0 divided by m over phi squared minus omega squared times cosine omega t. Okay, and so if it turns out that they do match, so if you're forcing it at its intrinsic frequency, then your particular solution turns out to be f0 divided by m over, and then obviously we can't have the same denominator if omega is equal to phi because you'd get a 0 in the denominator. And it turns out to be 2 phi, but then you have t times sine omega t. So this is very interesting here. So we already saw what happens if you match the intrinsic frequency with the forcing frequency. You get resonance. And so that's exactly what's happening right here. So take a look at this one. Our amplitude envelope, A of t, looks like some constant times t. It grows linear in t, and so it is going to be unbounded. Okay, and so this is indicating resonance. Now, in the case of when they don't match, right here, all you have is a constant. And so that means the solution is going to be bounded, as opposed to in the other case. So, oh, and I guess I should point out that both of these solutions here would be obtained by undetermined coefficients. That's how I work those out. I wouldn't expect you to memorize these formulas. I'm just writing them down so that I can, talk qualitatively about the interpretations that they have and stuff like that. So this is all for the undamped case. Now, for the damped case, let's see. Well, then, true, unbounded resonance cannot occur. So, and in this case, it's whoops, not all determined by whether or not they match exactly. So instead, what we see is that we get that the particular solution looks like C omega times cosine omega t minus delta. So it's going to, so the long-term solution here is going to have the forcing frequency, and that sort of makes sense, right? So if you're forcing on a system, after a long time, really all the system sees is how you're forcing it. That's kind of like the moral of this little formula here. But the other thing that's cool is that this C omega, what it looks like, this expression, it's a bit of a beast. It's got K minus M omega squared quantity squared plus C omega quantity squared, all in a square root in the denominator under your F naught. And so this is constant with respect to t, but it can be tuned for some devices. So if it's the case that C is at least square root of 2km, then the picture that we see for what this C function, that, by the way, this is a small c. It's going to look monotonically decaying, and it's not so interesting, right? But if we have the case where little c is strictly less than square root 2km, then the picture looks much more interesting. It goes like this. It will have one maximum, and then it'll decrease monotonically to 0. And so this, so the idea is that if you can tweak your omega correctly, then you can figure out. So this is showing the amplitude, right? This curve, it's not with respect to time here. This axis here is omega, and so if you push, say, envision your little brother's on a swing and you're pushing him. Like if you give him like a really slow push like this, you never get him going all that high, right? He doesn't swing up all that high. And then also if you go down here and you're like vibrating him really quickly, you're like pushing him really pushing him forward, then backward and forward and backward and forward and backward before he can actually like swing out. Well, he's not going to go very high. But if you find somewhere right in here in the sweet spot, then you're going to be pushing him at some speed that works with the internal parameters of the system, and his amplitude is going to get real big. So he'll be swinging really, really high. Now, he's not going to go crazy and go flying over the bars like everybody talked about in elementary school. But you can get him going pretty high. And in fact, this is the way that AM circuits are tuned in radios, in AM radios. So what happens is the tuning circuit drives the sound circuit, and when you twist the dial on the box, you're adjusting the capacitor basically to maximize the resonance and boost the signal as much as possible, so you can hear the radio better. Oh, and I just wanted to say one last thing, and that is, so I was talking about how after a while all you see is just the result of the forcing. And so in this case, so for a damped oscillator, your solution in general is going to have something where there will be the e to the minus pt, and then you'll have your sines and cosines, and the initial conditions will give you some cosine vt minus delta, something like that, right? Specified by initial conditions. And then you will have your term that's coming from the forcing. And you can see that because of the exponential right here, this term is going to be transient. It's going to go away. And so in the end, all that will be left is this term right here. And so this is called the steady periodic part. And so sometimes this will be denoted by like x sub sp or something like that. For us, just note that it's the particular part of the solution. So we can just call it xp.